In the previous video, we saw switching as a concept and covered two types of switching, circuit and packet. But first, let me see how much you remember. Switching is a neat solution to scale up networks. You can interconnect multiple networks through switches and thereby form a much bigger network. There are two types of switching, circuit and packet. In circuit switching, the resources, typically the bandwidth of the link, is dedicated for a given user, whereas in packet switching, these resources are allocated based on demand. And statistical multiplexing is the concept that underlines packet switching, and this results in a store and forward design. So this is being kind of captured here in this particular picture. So packets come, they get interleaved in the buffer, and on a first come first served basis, you serve the packets. One question we left hanging in the previous video was, when packets come, how are they forwarded to the right outgoing port? I just mentioned that they should carry some information in their header. So what is this information and how is this information used for forwarding? How this is done, there are three different types of packet switching: datagram, virtual circuit and source routing. So we will look at each in turn. Datagram switching is also called connectionless switching. This is because in circuit switching, you establish a connection before you can send packets. Here, there is no such connection established. Packets can be sent anytime, anywhere. So in circuit switching, during the setup time, you figured out through some process on which output port to send this particular packet. But here, since there is no connection setup time, somehow this information has to be conveyed, and this, I mentioned earlier, is conveyed through a destination address which is part of the packet itself. Destination address is the crux to forwarding, but often sender address is also included so that the receiver can reply to the sender. Fine, I have a destination address in my packet, but how does this help me determine which output port to send this packet? So for this, you need something called a forwarding table which maps these addresses to outgoing ports. And how are entries in this forwarding table filled? There are basically some protocols that run in the background, like routing protocols, learning bridges, that figure out these entries. We will see more of these in the upcoming videos. For now, assume that such a forwarding table is available and it is filled by some background process. This example will make things clear. So here we have multiple networks, LAN segments, interconnected through switches. These switches also connect hosts. Let's look from the perspective of switch 2. Here I have listed the forwarding table at switch 2. This, as I said, is determined through some routing protocol. Now suppose host H were to send a packet to host A. This packet will come on port 2 for the switch 2. Now what it does, it is going to look at the destination address, which is A. Then it will refer to this forwarding table. It says in order to reach A, use port 0. So it will take that packet and forward it on port 0. It is not shown here, but switch 1 will also consult its own forwarding table and figure out that to reach host A, this packet has to go out on this port, and since it transmits on this Ethernet segment, host A will receive the packet. So a very simple process. You can send a packet anywhere and at any time. This is because the packet contains all the information that is needed to forward the packet. This information is the destination address. So you don't need to set up any connection before you send the packet. So there is no call setup delay. Not only that, you don't have to maintain any per connection state. So a switch doesn't have to be bothered with maintaining state that, okay, A is talking with H or B is talking with C. It doesn't need this kind of state maintenance. All it maintains is to reach this particular destination, which port to send it on. So the state maintenance can be rather cumbersome in the internet core, where there can be millions of connections going through a router. So this is not a desirable feature, maintaining per connection state. Since datagram switching doesn't maintain, that's a very good feature of datagram switching. One drawback of datagram switching is that it provides no guarantees for packet delivery. Because there is no connection setup, you have no idea of determining the status of the receiver. You just send the packets. If the receiver is down, then you cannot deliver the packets to the receiver. Another problem with datagram switching is the possibility of reordering. For example, you are trying to reach destination D. When a packet comes, the routing protocol said send it out on this. Suppose this switch were to fail, then the routing protocol will figure out that something wrong has happened and it is going to find an alternate path, so the other packets that are coming can potentially be sent along this path. So packets can take different paths based on what's happening in the topology. This can lead to reordering. While the above reordering is a pain, the fact that you can find alternate routes makes the system very fault tolerant, and this is one of the other big advantage of datagram switching. You can always find alternate routes and cope with failure of switches. So that's with datagram switching. Let's look at virtual circuit switching. So originally the datagram switching was what was employed over the packet switching core. This was in 1970s, but in late 1980s and early 1990s, it was felt that the packet switching, the datagram switching over packet switching cannot support real-time applications like audio or video because these applications have delay constraints. By which I mean a packet has to reach the destination before some designated time. And if there are many packets ahead in the queue at a switch, this packet, the real-time packet, can get delayed. So this is not desirable. So as a trade-off between datagram packet switching and pure circuit switching, a virtual circuit switching was proposed. This found use in different technologies, ATM, frame relay, X.25, so on and so forth. So a point to note is virtual circuit switching operates over a packet switching core, by which I mean underlying this is the store and forward architecture. So the store and forward architecture supports applications that do not need any resource reservation, but if your application needs resource reservation, you can take a connection oriented approach through this use of virtual circuit switching. So basically in virtual circuit switching, a connection much like in circuit switching is established between the source and destination before you can send packets. And while this connection is being established, you can reserve any resources that this particular application flow requires. Since you are operating on a packet switching core, the packets that you are sending to a switch need to carry some information on what to do with this particular packet. This is done through what is called a virtual circuit identifier, VCI tag. This is carried inside the header of packets. So here is what happens. Before you send any data, you need to set up a connection between the source and the destination. And at each switch between the source and the destination, this is what you're going to do. You look at what the destination address is, and based on this, you create a mapping between an incoming VCI port to outgoing VCI port. All this will become clear shortly when I cover an example. The point to note here is the later packets that come will not carry a destination address but will carry a VCI tag. As part of this connection setup itself, as at each switch, you may also reserve resources. A point to note here is that a switch for a given connection, the VCI on a port has to be unique. This uniqueness is local in scope. In other words, this should be unique only at the switch. The same VCI could potentially be used at some other switch. Note that the same cannot be said about addresses used in datagram switching. The addresses have to be unique to ensure that the forwarding path takes the right path. Whereas here, the VCIs that you are using need not be unique across switches, but they need to be unique on a given port at a particular switch. Again, this will become clear through an example. And since this VCI is local in scope, this field can be much smaller. In other words, the number of bits that you need to represent this tag is going to be much smaller than the address field used in datagram switching, because this is global in scope. This has to be unique across all the hosts, whereas this needs to be unique across only the connections that are passing at a particular switch on a given port. So this example should clarify whatever was covered so far. So in this example, host A wants to send packets to host B. Before it sends these packets, it's going to establish a connection. So for that, host A will contact switch 1 and say, I want to talk with host B. Now the switch 1 is going to notice that host A packet has come on port 2, so it maintains what is called a connection table. Within this table, it is going to note that when a packet comes on port 2 corresponding to this particular connection, I will assign it a VCI of 6. And then it is going to notice that the destination is B. To reach B, it has to send it on port 1. This information it gathers much like in datagram switching through the forwarding table. So it does have a connection table as well as a forwarding table. The forwarding table tells to reach B, you need to send it out on port 1. So this connection table, it is going to fill that information. It doesn't know which out VCI to use. This will become clear shortly. And then it is going to pass this packet to switch 2. Similarly, switch 2 will notice that this packet has come on port 3. So it will note the input port as 3 and it is going to assign 5 as the VCI corresponding to this particular connection. And through the forwarding table, it will figure that this packet has to go on port 2. Thereby, it will set the output port to 2. Out VCI, it doesn't know. And similarly, at switch 3, it will note the in port as 3 and this is something that the switch 3 is assigning, and it decides that to reach host B, it needs to send it out on port 1, so it is going to put the output port as 1. Now when this connection setup packet which has traveled like this has reached host B, now host B, if it decides to accept the connection, it will allocate a VCI of, in this case 3, to identify the flow from A. Now what B does is it in turn acknowledges this connection, and when it is acknowledging this connection, it will specify to switch 3 that I have assigned a VCI of 3 for this particular connection. Thereby the switch 3 is going to fill the out VCI here based on 3. In other words, this is telling that if you want, B is telling switch 3 that if you want to send me packets from host A, use an identifier 3. That is how I identify the connection from A. So that's why it is put out VCI as 3. Similarly, switch 3, because it used an in VCI of 5, it is going to tell switch 2 to use an out VCI of 5. So this gets represented here, and similarly this gets represented here. So point to note here is that the same VCI 5 is being used at the different switches. So this is local in scope and not global in scope. Now as this ACK from B propagates back to host A, all these out VCI fields are filled up as shown here. Now forwarding of packet is very straightforward. So when host A assembles a packet to host B, it is going to put a VCI of 6 and send it to switch 1. Now switch 1 is going to now consult the connection table, and within this table it is going to see that this packet has come on port 2 with VCI 6, which means I have to send it out on port 1 and with VCI 5. In fact, this is the table you should look at. So this is going to forward this particular packet, but it is going to replace this VCI 6 with VCI 5. Now when switch 2 comes, again it's going to look at the connection table. So this packet has come on port 3 with VCI 5, which means I have to send it out on port 2 with VCI 5. So then it's again going to send this packet, but it will change the VCI from this to this. In this case it turns out to be the same, but if it were different it would change it. And similarly at switch 3, when it is going to send it out to host B, it changes the VCI to 3. So if you notice, the forwarding table is not being looked at to forward the packet, only the connection table is being looked at. So why maintain two tables in virtual circuit switching? So one is through the connection table, this connection establishment itself. Based on this, you can potentially reserve the resources. That is in fact the main reason. When you get this packet on port 2 with incoming VCI, you may decide that this has certain priority and thereby let me send it ahead of any other packet. So some such rules can be applied. Another big advantage of maintaining a connection table is that the switching can be done in hardware, whereby the switching speeds can be increased significantly. Looking up at a forwarding table, again this will become clear more when we cover the IP protocol, but this can be rather tedious. So here, through maintaining this in hardware itself, you can quickly send packets very fast across the switches. So that is another advantage of virtual circuit switching. So here are the characteristics of virtual circuit switching. Basically, through this use, you can reserve resources during the setup phase, and these resources could be buffer space, the amount of space in the queue, or the link bandwidth itself. Now, before you can send the first packet in your connection, how much time do you have to wait in virtual circuit switching? Because of this connection setup, this packet has to go all the way to the destination and the ACK has to come all the way back before you can send a packet. So this can take at least one round trip time. And another thing which is nice about virtual circuit switching is it has less per packet overhead. The VCI tag is much smaller than the address tag that is being used in datagram switching. But the biggest disadvantage is if something failed, the switch failed, all the old connections need to be toned down and a new connection needs to be established. So this is not as fault tolerant as datagram switching. So that's with virtual circuit switching. Let's move on to the next, source routing. In source routing, all the information that you need to route the packet is provided as part of the packet itself. So this is rarely used in practice because this places lot of responsibility on the source, because source now has to figure out the entire path. So this is illustrated in this figure. So host A, if it wants to send a packet to host B, will specify what all ports this packet has to go through. So it sends to switch 1 and it is telling send it out on port 1. So this goes like this. Typically this is rotated so that switch 2 can now act on this field. So this is put at the head. So switch 2 will know to send it out on port 2, and when it comes again this is rotated. So switch 3 will know that it has to send it out on port 3. So this entire path is specified. As mentioned, this is rarely used in practice because the source, which are typically hosts, have to run the routing protocol, and routing protocols can be rather complex because you are trying to figure out a route when there are millions of hosts out there and nearly thousands of switches that are out there. So where is it used in? Sometimes it is used in the internet core in the routers. So for example, in this case, there are multiple paths in this fashion. So this is all, these are routers, and this is the internet core, and when you are getting packets from this router, you may want to send it on this path, and when you are getting packets on this router, you may want to send it out on this path. If you want to enforce such a path, for example for load balancing purposes, you need to specify the path to take, and this is done through source routing. I have already mentioned that the source needs to determine the route. This is not practical in many situations. Another characteristic of source routing is that the header can be variable. Why is this the case? Depending on the destination, the path that you are going to take may vary. If really required, this feature can be supported both in datagram and virtual circuit networks, by which I mean that in datagram switching, for example, if the header contains the entire path, you can rely on it and not look at the forwarding table to send this particular packet. So this is a feature that can potentially be supported. And there are two types of source routing. One is called strict, in which the entire path is specified. Another is called loose, where only a subset of the nodes are specified. What do I mean by this is this route will say cover these nodes, but in between what nodes to cover, the path to take is not specified. All it says is this packet has to go through these nodes. Now that we have seen the different switching techniques, let's compare them along different dimensions. The first is the forwarding cost. What do I mean by this? Basically, the effort involved in determining which outgoing port an incoming packet has to be sent on. This cost is rather high for datagram networks because the forwarding table that you consult, this table typically is going to be rather long because it needs to carry the destination addresses of the many hosts that are out there. So the table lookup can be rather expensive in terms of time. On the other hand, in pure circuit switching, if a dedicated wire is allocated to the particular connection, there is absolutely no forwarding cost because the packets will just zip past one hop to the other. This switch, as soon as it receives one bit from the incoming line, can put it out on the outgoing line. In virtual circuit switching, this cost can be very low because you are now going to look only at the connection table. So this address looking in the forwarding table was done as part of the connection setup itself. So these costs do not arise as part of the packet forwarding. They happen during the connection setup. During packet forwarding, you just look at the connection table. Since the number of entries in this is local in scope relative to how many connections are passing through the switch, this can be made very small. As I have already mentioned before, this can also be implemented in hardware, thereby making it rather fast. In terms of bandwidth utilization, the datagram has the highest bandwidth utilization because it employs statistical multiplexing. In pure circuit switching, this is low because you are giving dedicated access to the resources. If a user is not using it, the resources will go waste. In virtual circuit switching, because you're using a combination of circuit switching and packet switching, this can be made flexible. In other words, only for those flows that need reservations you reserve. For the rest of the flow, they just do statistical multiplexing. In terms of per packet header, which among these three techniques has the lowest overhead? That's right, pure circuit switching, because the packets don't even carry any information as part of it. This is rather high because the address that you use is global in scope, so it will need more number of bits than in virtual circuit where you are using VCI, which is local in scope. In terms of resource reservation, this is not even possible in datagram. As in pure circuit as well as virtual circuit, this is possible. In terms of initial delay, that is before you send the first packet, the amount of time you have to wait, which has the least amount of initial delay? Right, datagram, because as soon as you get a packet, you can just forward it because the packet contains enough information to forward the packet to the destination. Whereas in pure circuit as well as virtual circuit, this is high because the connection has to be established before you can send the first packet. So reordering in datagram, it is possible because, as I said, if some switch failed, you can do an alternate path, whereas in pure circuit as well as virtual circuit, this does not arise because you are pinning the path. In light of the above, which provides the highest fault tolerance? That's right, datagram, because you can always find alternate path, whereas here if something failed, you have to establish a new connection. So that's with respect to trade-offs. A point I should mention here is even though virtual circuit was proposed as a compromise between pure circuit and datagram switching, it never really caught on in the internet because this is rather complex. So to this day, there isn't really that much support for real-time applications in the internet, but this is an ongoing research area. So to summarize, there are three types of packet switching that we saw: datagram, virtual circuit, and source routing. And there are inherent trade-offs between all these techniques. All this is theory. Up ahead, we will see how this theory is applied in practice in the Ethernet standard via Ethernet switching.